Do you still hold on to the belief that Pluto is the ninth planet of our solar system? If that is the case, you might want to delve deeper into our exploration today, because the next hour is dedicated entirely to this enigmatic world. We are talking about the potential ninth planet, a massive entity that could possess 10 times the mass of our Earth, wandering in the dark reaches of space hundreds of times further from the Sun than Neptune. If it truly exists, its discovery would fundamentally overturn our current perspective on the solar system and force a complete rewrite of the narrative surrounding how planets form and evolve. Let us examine the strange clues left behind and bring this invisible giant into the light through a bold scientific exploration. The story began in the winter of 1930, when a young amateur astronomer named Clyde Tombaugh, working at the Lowell Observatory in Arizona, peered through a telescope and spotted a faint speck of light drifting slowly against the backdrop of the stars. After weeks of meticulous study and comparison of photographic plates, the announcement was made: a new planet had been found. The world erupted in celebration. For the first time in nearly a century, the solar system welcomed a new member, named Pluto after the Roman god of the underworld, a fitting tribute to its dark and distant domain. Thus, the ninth planet was born, making headlines across the globe and sparking a sense of collective wonder. This is a long tale, one we will explore deeply, but before we begin, remember to support our journey of discovery. This was an era of grand exploration where science and mystery often walked hand in hand. Pluto entered textbooks and atlases, serving as the final chapter of our planetary family. And children learned its name alongside Mercury, Venus, and Earth. Initially, people assumed it was enormous. In fact, early estimates of its size were incredibly inaccurate. Astronomers were searching for what they called Planet X, a vast unknown world believed to be disturbing the orbits of Uranus and Neptune. They expected to find a behemoth, perhaps even heavier than Earth. This was what their theories predicted, and when Pluto was discovered, it was squeezed into that role. At least for a time, it fit the narrative. However, in the following decades, as telescopes improved and observational techniques became more precise, astronomers noticed something strange. Pluto did not seem large enough to account for the gravitational effects they were trying to explain. In truth, it was not just a little small, it was astonishingly tiny. Eventually, it became clear that Pluto was smaller than our own moon, which was the first major crack in its identity as a planet. Generally, a planet is expected to be larger than a satellite. Then came the issue of its orbit. Pluto's path around the Sun is not neat and orderly like that of the other planets. While the major planets trace nearly circular orbits on the same plane, Pluto follows a different line entirely. Its orbit is tilted significantly relative to the plane followed by most planets. Even more peculiar is how elongated its path is. During its 248-year journey around the Sun, Pluto actually spends about 20 years closer to the Sun than Neptune. Between the late 70s and late 90s, Pluto briefly became the eighth planet in terms of distance, pushing Neptune to the back. Astronomers found this unusual, but the public did not seem to mind. Pluto had already secured its place in popular culture with its own personality and mystery. Even Disney named a cartoon dog after it shortly after its discovery. Generations of students drew Pluto as a cold, lonely prisoner spinning on the edge of everything. Its oddity only made it more charming. Pluto was not like the other planets, but that was precisely what made it special. As the space age dawned, scientists began to realize that the solar system was far more bizarre and complex than they had imagined. The discovery of the asteroid belt in the 19th century had already forced a rethink of what constitutes a planet, and now the outer solar system was yielding new surprises. In 1978, another twist appeared when Pluto was found to have a moon called Charon. But this was no ordinary satellite. Charon is massive, nearly half the size of Pluto itself. Their masses are so close that they do not move like the Earth and the Moon. Instead of Charon orbiting Pluto, both bodies rotate around a common center of mass located outside Pluto's surface. This strange configuration led some to suggest that Pluto and Charon should be viewed as a double planet system. Once again, Pluto defied easy classification. Throughout the late 20th century, Pluto held onto its title. Probes were sent to study other planets, but none had reached Pluto yet. It remained a distant enigma, unvisited and unexplored. Astronomers occasionally whispered about its strange nature, but these debates rarely left academic circles. To most people, Pluto was a planet and always would be. Yet, scientific unease was growing. With technological progress, telescopes began to capture more objects in Pluto's neighborhood, small icy worlds scattered beyond Neptune. This region became known as the Kuiper Belt, and Pluto was not alone there. In fact, it was just one of many members. It was still the largest known, but not by much. The uniqueness that once set Pluto apart began to fade, and this cold, distant world started to look less like a lonely planet and more like just one member of a crowd. The turning point came in August 2006, when hundreds of astronomers gathered in Prague for the International Astronomical Union General Assembly. This meeting would become the most debated in modern astronomical history. At the heart of the controversy was a question that had followed Pluto for decades: what actually qualifies as a planet? By the early 21st century, discoveries beyond Neptune were accelerating. More objects similar to Pluto were found, including one that appeared even larger, named Eris. Eris is an icy body orbiting in the far reaches of the solar system, sometimes 3 times further from the Sun than Pluto. Early estimates suggested Eris was more massive than Pluto. If Pluto was a planet, then Eris surely had to be one as well. But adding Eris and potentially hundreds of similar objects to the planetary list created a problem. The public's view of the solar system had been stable for a long time. This led to the official need to define the word planet once and for all. Before this, there had never been a formal scientific definition. Everyone thought they understood it, but when asked for a clear explanation, the answers varied. Some looked at size, others at motion, and some at composition. Without clear standards, everything was held together by tradition rather than science. In Prague, the debate became intense, mixing scientific discourse with emotion. For many, Pluto was a cultural icon that had been a planet for 75 years. To change that felt like erasing something personal. Nevertheless, a final definition was submitted for a vote. According to the new resolution, a body must meet 3 criteria to be considered a planet: it must orbit the Sun, it must have enough mass to be pulled into a nearly spherical shape by its own gravity, and it must have cleared the neighborhood around its orbit. This third point means it must be gravitationally dominant, not sharing its orbital space with other objects of similar size. Under this new definition, Pluto passed the first 2 but failed the third. Pluto shares its orbital neighborhood with many other icy bodies in the Kuiper Belt. It has not cleared its path, nor is it the dominant force in its orbit. Thus, Pluto was no longer a planet. It was given a new label: dwarf planet. This category also included Ceres and Eris. The reaction was immediate and divided. While some scientists welcomed the clarity, the public was largely unhappy. Protests emerged, and the news sparked a global discussion about scientific authority. Does the location of a celestial body matter more than its physical nature? To some, like those leading the New Horizons mission, Pluto's scientific importance never changed, only the label did. The story of Pluto and the search for the true ninth planet continues to evolve. We have learned from history, such as when Ceres was downgraded from a planet to an asteroid in the 19th century, that our understanding of the cosmos is never static. Recent discoveries of extreme trans-Neptunian objects have revealed even more anomalies. These distant icy bodies follow strange, clustered orbits that do not align with the rest of the solar system. Their paths are stretched like long rubber bands, suggesting that something massive and unseen is tugging on them from the shadows. This clustering points to a hidden influence, perhaps a massive undetected planet carving out the architecture of the outer solar system. While we haven't seen it yet, the evidence is mounting. We are once again in an era of discovery, where the boundaries of our celestial neighborhood are being pushed further than ever before, reminding us that the universe still holds many secrets waiting to be brought into the light. However, computer simulations reveal that such a series of alignments happening purely by chance is extremely unlikely. There must be an underlying reason, and theories began to emerge in abundance. Among them, one idea stands out: the existence of a massive, distant planet. This became the foundation for the Planet 9 hypothesis. If a planet with a mass between 5 and 10 times that of Earth were orbiting far beyond Neptune, it could explain these phenomena. Its gravity would act like a shepherd, herding distant objects into place over millions of years and guiding their orbits so they never intersect with its own, yet always feel its persistent tug. But this poses a new problem: finding new distant objects is hard enough, and finding the hidden planet causing these effects is even harder. The outer solar system is vast beyond measure and filled with stars. A cold, tiny planet located hundreds of units away would be incredibly faint. If it happened to be on the opposite side of the Sun, it could remain hidden in the dark for many years. Some scientists remain cautious, pointing to the possibility of observational bias. Telescopes scan certain areas of the sky more frequently, which might make these objects only appear to be clustered even if they are not. Yet, even after correcting for these factors, the pattern of deviation persists. These distant worlds remain one of the greatest mysteries of our solar system. Their orbits hint at something that does not fit our standard planetary models, yet for now, they continue to circulate in darkness, silence, and isolation. In early 2016, Konstantin Batygin and Mike Brown published a paper that reignited the long-standing question: is there an invisible giant lurking far beyond Neptune? They ran extensive simulations, first including only the 4 known gas giants, to see how distant objects would evolve under their influence over time. The results showed that any prior alignment would dissipate, the clustering would not last. Then, they introduced a hypothetical 9th planet into the system, one with a highly elliptical, tilted orbit far from the Sun. Suddenly, the clustering returned. These distant objects maintained their positions as if performing a synchronized dance. This model matched real-world data far better than the hypothesis of random chance. While it did not explain every single detail, it strongly suggested that something massive and unseen is shaping the orbits of these remote celestial bodies. The announcement caused a sensation in both the academic world and the public, with the media quickly naming it Planet 9. This was partly because Brown had played a key role in the reclassification of Pluto, and now he was leading the push for a potential new planet much larger than Earth. Subsequently, a wave of attention followed. Other researchers began re-examining old survey data for missed clues, and new observation plans were developed to target the regions where Planet 9 might be hiding. Theoretical research surged, exploring how it formed, where it might be now, and its impact on the evolution of the solar system. One major advantage of the Bodigan and Brown proposal is its predictive power. It doesn't just explain existing objects but predicts where new ones should be found. The power of simulation lies in turning uncertainty into a structured problem. We are no longer guessing blindly. Instead, we define a range of possible parameters for Planet 9 and compare them against an ever-growing library of observations. It is a feedback loop where new sightings guide new simulations, which in turn point to where we should look next. Every step brings the image into sharper focus, even if the planet itself has yet to appear. Of course, these models rely heavily on what we have seen so far. If the known distant objects are just the tip of the iceberg, or if their parameters are biased, the models will be skewed. Therefore, astronomers remain careful. They do not claim the planet is definitely there, only that under current data, a planet with a specific mass and orbit is the best explanation. To understand how Planet 9 might herd these objects, astronomers use the analogy of shepherd moons in Saturn's rings. In those rings, tiny moons like Prometheus and Pandora act as guardians, their gravity shaping the edges of the rings and preventing particles from spreading out. As the rings orbit Saturn, these small moons give them slight, persistent tugs that accumulate over time to keep the rings bound and stable. If we replace Saturn with the Sun and the ice particles with scattered worlds far beyond Pluto, we have the scenario for Planet 9. Like a shepherd moon, its gravity gently shapes the orbits of the scattered objects around it. The difference is the scale. The distance between Planet 9 and its flock is not thousands of kilometers, but potentially hundreds of astronomical units. Its influence is slow and enduring, reshaping paths over millions of years of subtle gravitational pulling. For decades, the Kuiper Belt was viewed as the true final frontier of the solar system, a disk of icy bodies left over from the early solar system. But this snowy realm is not without its own strange features. Extending out to about 50 units from the Sun, the number of Kuiper Belt objects suddenly drops off. Astronomers call this sharp decline the Kuiper Cliff. Surveys find many small worlds within this range, but further out, the population plummets. This is not a gradual thinning but a sudden, cliff-like decrease. This has always raised questions: is the cliff real, or is it a limitation of our telescopes? Does the belt truly end there, or is something we cannot see still present? While visibility was initially blamed, more sensitive surveys have shown that the drop persists even after accounting for distance and brightness. If the solar system originated from a rotating disk of gas and dust that extended far beyond Neptune, why would it end so abruptly? Planet 9 offers a possibility. If it exists, it may have influenced the structure of the Kuiper Belt during the early shaping of the solar system. Its gravity would have moved objects that should have settled in this region, creating a void. Simulations suggest that Planet 9 could have pushed objects into more distant scattered paths or inward toward the Sun, leaving a hollowed-out zone. This wasn't a violent clearing but a gradual reconstruction over millions of years. This cliff remains one of the most tantalizing clues. It is a large-scale structural feature visible across multiple surveys, making it harder to dismiss as a mere coincidence or a bias in data. It is like seeing a long trench on the ground. Intuition suggests something massive was dragged across it, even if the culprit is no longer in sight. If Planet 9 or other unknown factors have indeed tilted these distant worlds, the outer Kuiper Belt might still exist, just not where we usually look. This is exactly where the Vera Rubin Observatory comes into play. With its unprecedented wide field scan and sensitivity, it will open a new window into the outer solar system. If the Kuiper cliff is hiding something, be it tilted distant objects or the elusive planet itself, this may be our best chance to find it. For now, the cliff remains a stark blank space, a sudden pause where the solar system seems to stop between the known territory of Neptune and the strange frontiers of the extreme populations. For centuries, the fact that our planets orbit in a roughly flat plane seemed so natural it was taken for granted. However, when astronomers compare the Sun's rotational equator with the average orbital plane of the planets, a small but real mismatch appears. The Sun's axis is tilted by about 6 degrees relative to the planetary plane. Long considered a minor curiosity, this tilt may carry deeper meaning in the context of Planet 9. It all comes down to momentum, which in space acts like a memory. When the solar system formed from a spinning disk of gas and dust, the planets inherited that motion. If the Sun and the disk started together, why is there a 6-degree misalignment today? The Planet 9 hypothesis suggests that this distant mass has been twisting the entire system for billions of years. Imagine the solar system as a spinning plate, and Planet 9 as a heavy weight circling the edge at a steep angle. Its gravity exerts a tiny but constant torque, slowly tilting the entire system. Computer models show that a planet with roughly 6 times the mass of Earth on a tilted, distant orbit could produce exactly the 6-degree tilt we observe over the age of the solar system. This requires a persistent, distant force, not a one-time event like a passing star, but something that is still there, gently pulling even now. This reminds us that the solar system is not a collection of independent orbits, but a coupled, flexible structure where a hidden weight on the edge can tilt the whole masterpiece. Instead of a single large planet, some scientists propose the distributed mass hypothesis. This suggests that the gravity shaping the outer solar system comes from the collective influence of many smaller icy bodies. Rather than a single shepherd dog leading the sheep, it is more like an undulating landscape slowly changing a hiker's path. This idea is plausible because the outer solar system might be far more crowded than we realize. If there are hundreds of thousands of medium-sized objects out there, their combined gravity could mimic the effects of a large planet. However, the challenge is that the total mass required would be several times that of Earth, and our current estimates of the Kuiper Belt's mass are much lower. Unless we have severely underestimated the number of Moon-sized or Mars-sized objects hiding in the dark, this theory struggles to explain why we haven't spotted a single one of them yet. Furthermore, a single large planet provides a steady, predictable torque, whereas a swarm of smaller bodies might create a chaotic mess rather than the neat alignments we see. Another path of inquiry asks if our laws of gravity are incomplete. This points toward modified gravity theories, such as MOND, which suggest that at extremely weak gravitational scales, gravity might behave differently than Newton or Einstein predicted. Some simulations show that these modified formulas can recreate the clustering of distant objects without needing a ninth planet at all. However, these theories face high hurdles because general relativity has passed every high-precision test we have thrown at it within the inner solar system. While modified gravity is an elegant way to solve mysteries like dark matter, Planet 9 remains a simpler explanation that doesn't require rewriting the laws of nature. Historically, we have discovered outer planets by observing anomalies first and finding the hidden source later. If the search for a physical planet continues to fail while evidence of its influence grows, these alternative theories of gravity may gain more attention. Even more exotic is the idea that the source of this gravity isn't a planet at all, but a primordial black hole. We aren't talking about the monsters at the center of galaxies, but a tiny black hole perhaps the size of a grapefruit with the mass of the Earth. Such objects could have formed in the extreme density of the Big Bang and survived until today. A black hole of this mass would be only a few centimeters wide and completely invisible, yet it would exert the same gravitational pull as a planet. It wouldn't reflect light or emit heat, making it nearly impossible to see directly. Our only clues would be the rare moment it passes in front of a distant star, briefly magnifying its light through gravitational lensing. While this sounds like science fiction, it fits the mathematical models perfectly. Finally, there is the possibility that Planet 9 is a captured rogue planet. Stars are born in crowded nurseries, and in the gravitational chaos of those early environments. Planets are often thrown out of their home systems. If a drifting rogue planet passed near our young sun at just the right speed and angle, the sun could have captured it. This would explain its highly elliptical and tilted orbit, the classic signature of a cosmic outsider. That concludes our exploration for today. As we look toward the edge of the dark, we are reminded that even in our own celestial backyard, there are vast regions still waiting to be explored. Whether it is a giant planet, a swarm of icy worlds, or something even more mysterious, the truth is out there, circling in the silence. Thank you for joining this journey. Have a wonderful dream and a beautiful day. We will see you in the next episode.